A concept that was identified to give you guys some challenge was working with proportions and equations. Many of you find comfort in just plugging and chugging numbers and being able to get an answer, but when not given every number, you find a particular challenge in order to use a proportion that is not just directly proportional. In this unit, we had four major equations that compared charge, distance, and some variable. For example, we had the electrostatic force, and that was proportional to not just charge 1, but a second charge as well, all over d squared. We also took a look at an electric field and realized that each charge produced its own electric field, and that was proportional to an inverse d squared as well. The third that we took a look at was the electric potential energy, and we realized in this case it was proportional to Q1, Q2, all over D, and the final one, a voltage, was proportional to Q1 over D. So each charge had its own voltage, each charge had its own electric field, but all of these can be compared with proportions. Let's take a look at an example to show you what I mean. Here's an example problem using proportions. It says there are 30,000 volts of potential at a distance of 3 meters from a 10 microcoulomb charge. That is giving us our initial conditions, and we're able to identify that there are certain things here: a distance, a charge, and an initial voltage that we have. Now they're asking us if changes were made, so if the charge were doubled and the distance were cut in half, what would the new voltage be? Now in this problem, I gave us a little bit more initial information than we normally would be given, because I want to be able to show that we can solve this two different ways, one with numbers and one without, and you'll see the benefit of being able to answer it without. So for the first one, based off the initial conditions, I know I could solve for the voltage is equal to K times Q all over D. And so if I were to take a look at this, I can see 9 times 10 to the 9th. Now, the charge, they said, would like to be doubled. And so if the original charge was 10 microcoulombs, I would want to make it 20 microcoulombs, or in other words, 20 times 10 to the negative 6 coulombs. And then if the distance were cut in half, the original distance was 3 meters, so to cut that in half, I would go 1.5 meters. And I could go ahead and solve this, and I would end up with a grand total of 120,000 volts. Now this was just using a plug and chug method, something that we're very comfortable with. But something that we're a lot less comfortable with would actually be just using proportions. But I want to show you the power of that. So let's get rid of some of this work on here and take a look just using proportions, what we have. Now, we can start off with the initial condition, and we could say that the voltage, 30,000 volts, was produced when we had the original charge of 10 microcoulombs at a distance of 3 meters, the original distance. And so whatever we do to one side, we have to do to the other. So they say that they want to double the original charge, and they want to cut the other distance in half. So you can see that I have a coefficient of 2 over 1/2 added to the right-hand side. I would have to put that same coefficient on the left-hand side. Now, we know that 2 divided by 1/2 is actually 4. And so if I multiply that coefficient of 4 times my 30,000, I get, you got it, 120,000 volts. You can see that the solution of this problem using proportions, when given an initial condition, was way more straightforward than going ahead and plugging and chugging with numbers. Now, if you are comfortable with just the mathematics, that's fine. But what if I never told you how much charge we had? And And what if I never told you how much distance we were? And I just said there's 30,000 volts of potential at a certain distance from a charge. If the charge were doubled and the distance were cut in half, what's the new voltage? In this case, you can't just plug and chug. You would have to use this method in order to still be able to figure out the answer.